So in the previous session, we looked at random variables, and we did a few examples of random variables. And for some simple ones, we calculated the probability that a random variable might take a particular value. Okay? So, and recall that random variables are maps from the sample space to the real numbers. Okay. So if we have a discrete sample space and we map to the reals using a random variable, we call that random variable a discrete random variable. And we are interested in the probability that a random variable takes a particular value. So for that, we calculate what are called probability mass functions. So discrete random variables have probability mass functions, right? And we actually calculated one in the previous session. We just didn't give it that name. Okay? So we want to, this will assign a probability, which is the probability that a random variable takes a particular real, a value of a particular real number. Okay? So this is the idea. Let's say I have a discrete random variable capital X, right? It's a map from, it's a map from the sample space to the reals. Now I'm going to have what I call a probability mass function. And so if I'm using capital X for the random variable, I will use f sub capital X for the probability mass function, right? And that's the function such that f sub x evaluated at small x, the value of the random variable capital X, that's the probability that x is capital X, the random variable, takes that value small x. Okay? So that's what a probability mass function for a discrete random variable is. Okay? And like I said, we did an example last time. We'll do a few more examples here so you get comfortable with the idea. Okay? So what do I need? Because I'm talking about probabilities, I need that the probability that x takes the value capital X should be greater than or equal to 0 for all real numbers x. So we're mapping from reals to reals, okay? And it's a probability. Probabilities are never 0. Okay? The sum over all x, for all the admissible, all the values small x that the random variable capital X takes, if you sum over all the values that are in here, you're summing over probabilities. So those probabilities should sum to 1. Okay? And once again, the way we interpret this is this notation here, f sub capital X of small x, yes?
So does this mean that fx in a graph and some integral from a to b, that gives me the probability of a to b of a continuous variable?
Yeah, if we have a continuous random variable, then we will need integrals. But in the discrete case, we'll be using sums. Okay. All right, so we'll come to that in a bit. Okay. So let's work one out. Right? We're going to roll a 6-sided die once. Capital X is the random variable. it will take a value 1 if the roll gives a 6, and it will take the value minus 1 if the roll gives anything else. Okay? So it's a map from the sample space to the reals. Now, how would you assign the probability that the random variable is equal to 1?
1 by 6.
Okay. 1 by 6. Why?
Because x is 1 only when the die is a 6. There's only 1 or 6 chance of that.
Okay. X is equal to 1 is the same as the probability that 1 has rolled a 6. And if it's a fair die, then the probability of rolling a 6 is 1 out of 6. 1 outcome out of 6 equally likely outcomes. Okay, what's the probability that x is the random variable x takes the value minus 1? If you say 5 over 6. Why? Because the probability that x is equal to minus 1 is the probability of rolling something other than a 6. That's 5 outcomes out of 6 equally likely outcomes. So the probability that x is equal to minus 1 is 5 over 6. Okay? What's the probability that the random variable takes the value 0? 0, because the random variable only takes values plus 1 and minus 1. So there's no way that it can take the value 0. Okay? Okay, so in our notation now, for the probability mass function for this x, right, we write f sub capital X. F subscript, the name of the random variable, in this case it's x. So f sub x of 1 means the probability that x equals 1, and we agreed that that was 1/6. F sub x of minus 1 means the probability that x is equal to minus 1, and we agreed that that probability was 5/6. F sub x of 0 means the probability that x is equal to 0. So the probability that x takes the value 0 is 0 because x only takes values minus 1 and plus 1. Okay? Now, here's the probability mass function evaluated at certain inputs. Now, what I want to do is I want to give a description, or I want to give a definition for this probability mass function in such a way that whatever real number you give it, it gives the right probability. Okay? And if you give it a number that x cannot take, then it should give 0. Okay? Okay, so continuing with this discussion, this is what it would look like. This says the probability mass function for x, if you give it an input x equals 1, it puts out it gives you 1/6. The probability that x takes the value 1 is 1/6. If you give it the value minus 1, then it outputs 5/6, because the probability that x equals minus 1, we agreed, was 5/6. And if you give it any other input, well, the random variable x cannot take that value other than plus 1 and minus 1. So if you give it any other input, it outputs 0. Is that okay? All right, so that's the probability mass function for x. It's 0 for pretty well all the real numbers except for x equals 1 and x equals minus 1. Is that okay? Okay. So that was the probability mass function for a discrete random variable. And we will often use the abbreviation PMF for probability mass function. Okay? We also have the idea of a cumulative mass function for a discrete random variable. Okay? And I will often use the abbreviation CMF to mean cumulative mass function. Okay? And basically the cumulative mass function is accumulative probabilities below for some input. So the idea is that the PMF evaluated at x equals 37. So that's the probability that x takes the value of 37. But the CMF for some random variable evaluated at x equals 37 is the sum of all the probabilities up until x equals 37. So the probability that x is less than or equal to 37, that's what the CMF evaluated at 37 would give you.
So it's like sort of like the integral I was talking about.
Or it's a summation in this case. Okay? So this is how we define it. All right? So we have the random variable capital X. There is an associated probability mass function for this random variable. And the notation we use is small f subscript, the name of the random variable. And I will try and consistently use capital Latin letters for random variables. And then there's also an associated CMF. And for that, we will use capital F sub the name of the random variable. Okay? And these are the accumulative probabilities. So this is the probability. If you give it an input, small x, it outputs the probability that the random variable takes a value less than or equal to x, which is the same as summing over all the allowed values, t, all the values that this function capital X takes, all those allowed values t less than or equal to whatever x you're giving as the input. If you sum over all of those, that's the CMF evaluated at small x. Okay? Any questions about that? Yeah.
If we took the previous problem,
Yes.
the PDF where it was 1 at 6 and then like minus 1 at all other ones.
Yeah.
So if I took from 6, then it would be 1 minus 1 and then that.
Right. So let's look at the previous exercise and see how this idea, we'll do a few calculations for it. Okay, so what did we have? In the previous exercise, if we draw a graph for this, at x equals, let's see, the probability that x equals 1 was 1/6. The probability that x was equal to minus 1, somewhere here, was 5/6. Okay? Now, What if I ask you f sub x of 3? Okay, right. So what's capital F sub x of 3 means the cumulative probability, what's the probability that x is less than or equal to 3, right? So we write this. Well, whatever probability x is, well, so whatever value x is, it's either -1 or +1 after an experiment. So you're guaranteed to have values less than or equal to 3. So this must take the value 1. Is that okay? Okay.
So this will be 1 till 6 on the x-axis and then 1 and -1 on the y-axis. Because where that
Okay, on the y-axis, you don't have to really have negative values because probabilities are never negative, right?
probabilities is like x can take 1 to 6 as choices.
No, okay, no. I'm saying if we continue with the previous example, x takes the value +1 if you roll a 6. X takes the value -1 if you roll any other 1, 2, 3, 4, 5. Okay? X only takes values +1 and -1. So this notation means, what's the probability that x takes a value less than or equal to 3? Well, the two values that x can take are -1 and +1. So it must take a value less than or equal to 3. Okay? All right. Let's try another one. Sorry, f sub x of 0. Okay? Right. So this is the probability that x is less than or equal to 0. Well, the probability that x is less, x could be -1, that fits in here. X can't be 1, because that's bigger than 0. So the probability that x is less than or equal to 0, x less than or equal to 0 means necessarily that x took the value -1. What's the probability that x took the value -1? It's 5/6. Okay. How about f sub x of -1.1? Great. That's the probability that x is less than or equal to -1.1. But none of the allowed values of x, the only allowed values of x are -1 and +1, none of those are less than or equal to -1.1. So this is 0. Okay, so that's an example of, continuing on with our previous example, that's an example of doing, calculating the cumulative mass function for that random variable capital X at various values, inputs x. Okay? And we were able to think our way through it. We didn't actually have to use the formula. Okay? But let's do this one using the formula, okay? So the formula is that f sub x of x is equal to sum over all the allowed values of x, all the allowed values t that x might take, which are less than or equal to this x that you have specified. Okay? Times f sub x of t. So that's equal to, in our case, what are the two values? Well, right, f sub x of minus 1 plus f sub x of 1. Those are the two values that x takes, and they're both less than or equal to, so let's say we're doing 3. So you sum over all the allowed values that x can take, which are less than or equal to 3. Well, minus 1 is less than or equal to 3, plus 1 is less than or equal to 3. There's no other values that we have that x takes which are less than or equal to 3. Oh, okay. So that's 5, 6 plus 1, 6 equals 1. Okay? So that's a few values calculated for the CMF for different inputs based on the previous example. Okay, let's go on to a different example. Hey, you need to do a few of these to feel comfortable. Okay, consider rolling a 6-sided die. The random variable x takes the value of the roll. So now x can take values 1, 2, 3, 4, 5, 6. What's the probability that x is less than or equal to 4? Okay, well, the probability that x is less than or equal to 4 is the probability of rolling a 1, a 2, a 3, or a 4. What's that probability? 4 out of 6. Yeah. Okay. So in our notation, that would be f, capital F sub x of 4. That would mean this. Okay. All right. So we agreed that that was the solution. Okay. Now let's work out the PMF and the CMF. Okay, for this x. Okay. So we have x. We want to find its probability mass function. We want to find its cumulative mass function. Okay. So we need to give it a definition such that no matter what real number I put into it, whatever real number small x I put into it, it returns the probability that capital X takes that value. Okay? So let's see. So how would you define that? Right? So 1 over 6 when x is equal to 1, 2, 3, 4, 5, 6. Okay, so we've defined it at 6 real numbers. How do we define it for all the other infinitely many real numbers? There's 0 otherwise. Okay, that's the PMF, the probability mass function. Okay, now how do I find the CMF? Yeah.
You have to have like separate functions where we want to start with like probability 0 to values of x less than 1.
Right. Okay, so let's start by considering that these are, it's taking values 1, 2, 3, 4, 5, 6. So the suggestion is that we can dispose of all, we can work out for every input x, for x less than 1. Let's do that first, okay? So the CMF evaluated at x will be 0 if x is less than 1. Okay? Now, can you give it to me for another segment of the real line? Okay, so if x was allowed to be 1, then the probability would be 1 by 6. What about 1.5? It would be 1. The probability that x takes a value, how can x take a value less than or equal to 1.5? Well, when x is equal to 1, it's taking a value less than or equal to 1.5. And the probability of that is 1/6. Okay, what about 1.99? Same thing. Okay, so all the way from 1 to 2, but not touching 2, the probability of taking a value less than or equal to 1 is 1/6. Okay, so 1/6, so x is bigger than or equal to 1, well, we shouldn't touch 2. Okay. The CMF evaluated at 2 is what? Well, that's supposed to be the probability that x is less than or equal to 2, which means it could either be 1 or it could be 2. So what's the probability that x is equal to 1 or 2? It's 2/6. Okay, what about 2.5? What about 2.999? Yeah, okay. So 2 less than or equal to x less than 3. Is that okay? All right. Okay. So from 1 to 2, then 2 to 3. What about on the interval from including 3, but not including 4? Okay, so if I'm in here somewhere, what's the CMF evaluated there? Okay, that's the CM. That means the probability that x takes a value less than or equal to this number, which is the probability that x is equal to 1 or 2 or 3, well, 3 out of 6. Okay. Okay. What about numbers in somewhere over here? Well, the probability that x takes this number, or less than or equal to that number, is the probability that x is equal to 1, or 2, a 3, or a 4. And the probability of rolling a 1, a 2, a 3, or a 4 for a fair die is 4 out of 6. And that works right up until you reach 5. Yes?
So, because I was so start, so if I want to shorten the expression, can I just write f(x) equals to 0 if x is less than 1, or to range, I just write the floor of x is less than 1?
Yeah, you might be able to rewrite this using the floor function if you want. Yes? Okay. Let's say, okay, so now what about on the interval from x lies between 5 and 6? including 5, but not including 6. What's the probability? 5 out of 6, right? So if you're in this over here, then the probability that x takes a value less than or equal to that is the probability of rolling a 1 or a 2 or a 3 or a 4 or a 5, which is 5 out of 6. Okay. I've run out of space, so I'll continue up here. What's the probability? Okay, so what is the CMF evaluated at 6? It's 1 because that's the probability that x is less than or equal to 6. All the allowed values of x are less than or equal to 6, so that's 1. What about the CMF evaluated at 6.1? That's also 1 because all the allowed values of x are less than or equal to 6.1. Right? So once you've gone past the maximum value of x, I mean, if there's a maximum value of x for your random variable, then the CMF evaluated at numbers which are bigger than or equal to the maximum value of x, that should go to 1. So this will be 1 for x greater than or equal to 6. And okay, so it's defined for, I think now, for all of the real numbers. Okay. Okay, what's f sub x of 5? So I read down here, yeah, okay, f sub x of 5 is 5, 6. Is that okay? So your CMF is going to be something that's increasing as you go from left to right on the line. All right, so that was for, yes? The floor function jumps between, so when you get to 1, it jumps, and then it's constant, and then when it hits 2, it jumps again to 2, and it's constant, yeah. So it's kind of like dropping the decimals. Yeah. Yeah. Okay. For discrete random variables, capital X, we had a PMF called f sub x, small f sub x, and we had a CMF called capital F sub x. Okay. For continuous random variables, your sums turn into integrals. So we don't have a probability mass function. We have a probability density function. Okay, so you have a probability density function and you have a cumulative density function. Okay? Okay. So, and we can't look for the probability that x takes one value in a continuum. We look for the probability that x takes a value between a and b. Okay? So the probability density function for x is such that if you integrate it with inputs from x equals a to x equals b, this will give you the probability that the random variable capital X takes a value between a and b. If you have a continuous random capital X, the probability density function for that, small f sub x, is a function such that, well, the probability density at each point x has to be greater than or equal to 0. If I integrate from minus infinity to infinity, so before I summed over all the real numbers, right? So if I integrate from minus infinity to infinity f sub x dx, I should get 1. And if I integrate the PDF for capital X from small x equals a to small x equals b, that's the probability that x is taking a value between a and b. Okay, so those are the 3 properties. The probability density function, you can see they're analogous in some way to the properties for a PMF. Yes?
We cannot use probability density functions for situations like where we have discrete values, like the numbers of a dice, right?
Yeah, so if you're talking about a discrete sample space, it has discrete random variables, and those have probability mass functions. If you have a continuous sample space, then it has a continuous random variable, and that will have a probability density function. Yes?
So what if the discrete values are, I guess if there's a 100-sided dice,
Yes?
there's a lot of discrete.
Use integrals with discrete spaces if you wanted to, but if you wanted to do that, then you have to define probability density functions for your discrete space, and they would have to be defined with delta functions, and we don't want to do delta functions in this course. Okay. All right, so here's an example. Here's an example. So what does this look like? The graph of this thing. So we should draw that. Okay, so there's an example of a PDF for a particular kind of random variable, capital X. We're going to see this one again later. The graph looks like that, so it's got 2 pieces. So it's 0 for the negative values of x, and then it drops off exponentially from lambda for the positive values of x. Okay, so what do we want from a probability density function? We want all the values to be 0. All the outputs, we want all the outputs to be greater than or equal to 0. Okay, so this set of outputs is greater than 0, is equal to 0, and exponential function is never 0 or negative, right? And lambda is positive. So, okay? So that works. The other thing that you want is that this if you integrate this from minus infinity to infinity, you will get 1. Okay? Okay, so let's see about that. If I integrate from minus infinity to infinity, f sub x dx, okay? Now, this is going to happen a lot because quite often, these definitions come in pieces, right? So when something is coming in pieces, you want to break it up. So if you're saying it's defined like this over this interval, and it's defined like this over this interval, then break up your integral, right? So break it up into 2 pieces. And where's the change occurring? It's occurring at 0. So integrate from minus infinity to 0, and then integrate from 0 to infinity. Because it's defined differently on this interval, and the PDF is defined differently on that interval. Okay, so you want to do don't try and integrate it all in one piece. break it up into two pieces. Because the function is defined, the PDF is defined in two pieces. Okay. Well, what's the form for the PDF on the interval from minus infinity to 0? It's 0, right? So this part doesn't matter. So we can just integrate from 0 to infinity. Now, what's the form for the PDF on that interval? It's lambda e to the negative lambda x dx. Okay. Now, what's the integral of lambda e to the negative lambda x? Well, I can pull the lambda outside. What's the constant can be pulled outside the integral? What's the integral of e to the negative lambda x? Okay, so it's e to the negative lambda x divided by negative lambda. Does that work? Yeah? Yeah? Now, this is put to be evaluated at 0 and infinity. Is that okay? All right, you will need to know how to integrate this function. Okay. Well, okay, so let's make a simplification. I have lambda being divided by negative lambda. So that's a minus, right? Okay, so let's just make that minus 1. Okay. When I have a minus sign, I'm going to evaluating this at 0 and infinity. I can change the order of the evaluation and get rid of the minus sign. So instead of at infinity and 0, I can have 0 and at infinity picking up a minus sign. Okay? So the minus sign can go away, provided that I change the evaluation order. Okay. Yeah.
Can you please explain what is happening?
Yeah, if I have f of x evaluated at a and at b, I mean f of b minus f of a, right? If I have minus 1 times f of x evaluated at a and at b, that would be minus f of b plus f of a, which is f of a minus f of b. And that would be the same as evaluating f at x with the evaluation order interchanged. Okay? So evaluating minus something at infinity and 0 is the same as evaluating plus something at 0 and at infinity. You don't have to do that if you don't want to. It'll come out the same way. I just find it easier to think about it this way. Oh, the integral of e to the kx dx is equal to e to the kx over k, right? So that's what we did. It's e to the negative lambda x divided by negative lambda, and we had a lambda over here. And those cancel. Okay, any more questions about the integral so far? Okay, now, e to the negative lambda x as right? The exponential function evaluated at 0 is what? 1. Okay. And you have a decaying exponential function. The function is decaying exponentially. So in the limit as you go to infinity, what do you get? 0. Right? Evaluating at infinity means a limit. Yeah.
Sir, are you expected to know normalization? For example, lambda shambla nikaalne.
No. I mean, we are not normalizing. We are showing that this is normalized.
Okay, like will find the value of lambda or x less than lambda fx ये value है. So are you expected to know normalization
No.
to find lambda?
No. Okay. All right. All right. So as I said, this evaluates to 1. Okay? So it's doing what we want it to do. Right? The PDF always takes non-negative values. Integrating the PDF over the entire real line gives you 1. And so we could say that there's an exponential random variable. Well, we call it the exponential random variable, which has this PDF. Okay? All right, so that was the example of a PDF. Now, we talk about CDFs. So what would the CDF for some random variable be? Okay? So the cumulative distribution function, yeah. Yes.
You said the PDF always takes positive value, right? And integrate.
Oh, the PDF always takes values greater than or equal to 0. Okay. So for the CDF, for a continuous random variable, we use the notation capital F, subscript, the name of the random variable. And if you evaluate that at x, that's supposed to be the probability that x, the random variable, takes a value less than or equal to small x. Okay? Well, that means anywhere from minus infinity to small x. Well, how do we find that probability? We integrate from t equals minus infinity to t equals x, f sub x of t dt, the PDF. No. This is the CDF, and we can find the values of the CDF by integrating the PDF. Right, so we can find, if we have the PDF, we can get the CDF via integration. And if we have the CDF, we can find the PDF from derivatives.
Sir, we just integrated the functions to get PDF. Is that what we just did over here in that example over there?
In this calculation here? Well, okay, so that was, yeah, so this was this would be the function evaluated, the CDF evaluated at infinity. What's the probability that x is taking values from minus infinity to infinity? And that's equal to 1. Right, and that would be the CDF evaluated at infinity. Okay. Or in the limit as its input goes to infinity. Okay. All right, so let's say that we have this. We continue with this exponential random variable, which has this PDF. Okay? Now I want to define the CDF. Okay? The PDF comes in two pieces, so we're going to need at least two pieces to define the CDF. Okay? All right, so let's okay, so this is the PDF. It gives you a probability density. The CDF gives you a probability. Right? So in order to get the probability, you have to integrate the PDF. Okay? So the values that the CDF gives are given by integrations of the PDF. Right? The values that the CMF gives are given by summing values of the PMF. Okay. So let's think about this. Like I said, I might have to define this in pieces. What's the probability? Okay, so here's some value x which is negative. So f for this x, that's a probability that the random variable takes a value less than or equal to small x, and I'm specifying that small x is negative. So what's the probability that it takes, okay, that value? Well, we find probabilities by integrating the PDF, right? Here the interval then is from minus infinity to small x. So we have to integrate from minus infinity to small x, f sub x of t dt. Okay? Now, if x is less than 0, we're integrating 0. Right? Which is just going to give us 0. Okay? So this is going to be 0 for x less than or equal to 0. Oh, okay. Right? So we're saying, what's the area under the curve of the PDF from minus infinity to this x, which is negative? Well, the area under the curve is 0. Okay, so that's 0 for x less than or equal to 0. Okay, now let's suppose that there's some x out there. What's the probability? Well, what's the probability that capital X takes a value less than or equal to the small x? Well, it's the area under the curve, or the integral, from minus infinity up until this small x. Okay, all the way up to here it's 0, so I only need to integrate from 0 to this x. So now f sub x of small x, that's the integral from t equals 0 to t equals x, the probability density function, dt. Okay, well, that's equal to the integral from t equals 0 to t equals x, lambda e to the negative lambda t dt. So what's that? That's lambda e to the negative lambda t divided by negative lambda, evaluated at t equals 0 and t equals x. Can somebody tell me what that is? Okay, so remember the lambdas are canceling, and we've got a minus sign. So that's the same as e to the negative lambda t evaluated at t equals 0 and t equals x. Right, so that gives you 1 minus e to the negative lambda x. So 1 minus e to the negative lambda x for x greater than 0. Okay, that's the definition for that. And you just check, does this definition work for all of the real numbers? Okay, well, everything left of 0 and everything right of 0 has been covered. So it works for any real input. You can work out what the CDF is for any real input. Okay? So that's an example of a CDF being calculated from a PDF. Yes?
How do we get these functions in real life? Problem?
Okay? Okay, this one comes from, there's a discrete random variable called the Poisson random variable, and this is related to that. So there's some argument about where this comes from, but I'm just pulling this out of a hat to illustrate the definitions right now.
I was wondering, how do we know that this function that we have defined gives us the probability at each real number?
Oh, well, okay, well, if you look at the definition, whatever real number you put in for x, this is going to output something. So it's defined for all real numbers. And similarly, your CDF should be defined for all real numbers. Two things that you need to know about CDFs. One is, okay, sometimes you'll be given these random variables in tables, right? And if it's an important enough random variable to have a name and appear in the table, then you would be given, you may not be given its PDF, but you'll be given its CDF, right? And with the CDF, okay, so this probability that that x lies between A and B, it could be given to you. It could be given to you. You would, if you were given the PDF, you would do the integral. You would integrate the PDF from A to B. But if you were given the CDF, you would just have to do a subtraction. This is that x is less than or equal to b. Now, subtract off the probability that x is less than or equal to a, and what you're left with is that the probability from x equals a to x equals b. Okay? So the CDF is convenient in that if you've already you've basically done the integration of the PDF, that's in the CDF, and now you just have to do subtractions to work out your probabilities. So it's convenient to have the CDF around. The other thing is that since the CDF was given to you, sorry, the CDF is constructed by integrating a PDF, right? So if you take the derivative of the CDF, you can recover the PDF from it. So if you were to take the derivative of these two pieces of the CDF, you would get a definition for the PDF in two pieces. Okay? All right. Okay. I guess we can continue with expectations next time. Yes?
If we were to differentiate the CDF of 7 minus this differentiated CDF of 3, would we then get this PDF of the value that lies between 7 and 3?
Okay. Okay. If you want to, all right. Right. If you were to take the CDF and you were to differentiate it, that would give you the PDF. And now if you wanted to evaluate the probability between A and B, you could integrate that again. But since you already had the CDF, you could just take the CDF at B minus the CDF at A. Yes?
Just for clarification, the PDF gives you probability at an exact point.
The PDF, if you tried to use the PDF to get a value at an exact point, you would get 0 because you would be integrating from x equals A to x equals A.
Then PDF integrating just set up.
No, these are probability densities, they're not probabilities. Okay? See you next time.